Good morning, everyone. Welcome to another year of seminar, the Institute of Earth Sciences. I'll start with two very short announcements. Tomorrow on Thursday at 11 o'clock, the Atmosphere, Climate and Oceanography seminar, we have Michelle Flores, who will talk about the link between ocean biology and atmospheric sciences, or atmospheric processes. After the seminar today, I was asked to remind everyone at 12 o'clock we have the almost weekend meeting. There's coffee, cake, and maybe some biscuits as well. Sorry? Oh, and today especially with me to say goodbye to Karen Shoshana, who was the administrator in the department for many, many years, and she's moved on to bigger and better things. So now it's my pleasure to present Dr. Yohai Magen. He did his bachelor's here at UG in geology. He went on to do a PhD in Tel Aviv with Alon Ziv, Asaf Inbal, and Gilon Ber from the Geological Survey. He's since 2024 has been doing post at Scripps and with Alice Agnes Gabriel. And we'll hear about his research today, machine learning and aseismic.
Thank you. So today we're gonna talk on subductions and on aseismic sleep on those subductions, slow sleep event, and how we model them with physics-based modeling and machine learning. But maybe the takeaway home message I wanted to take from this talk is how when we want to model our Earth and we want to do it precisely on computer, very fast those models become very, very expensive. And how we can take those expensive models, take their output, put them into a machine learning model, and then approximate this model and make many inference of those models very, very fast, and what we can gain out of it. So I did my undergrad not only in geology but also in computer science, and I studied, I would say, on the borderline between geology and computer science, more into geology or geophysics. And in my undergrad, I studied earthquakes and fault modeling. When I took mainly this route, when I started with understanding how to process mainly satellite-based data in order to understand how our Earth is deformed. And from those deformation we gain from the satellite-based data, we try to understand how earthquake and faulting behave. This is the data-driven approach. What we're going to talk about today is the other way around. We will try to start with what we understand about fault and their physics and how they behave, and try to model them with numerical simulation to produce the observation that we have. And we will use machine learning in order to accelerate those numerical simulation. Our motivation to study subduction zone, I think is obvious in this crowd, is that those subduction zones produce the largest earthquakes in the world. They produce megathrust event, magnitude 9 and above, where two mentionable earthquakes in the recent future are the 2004 Indian Ocean earthquake that caused hundreds of thousands of fatalities, and the 2011 Tohoku earthquake in Japan that caused the collapse of the Fukushima reactor. So those are very devastating events that we want to understand how they occur. Generally, up until about 25 years or so, the classical view of faulting has been held in general and in subduction zone in particular, when we viewed a fault as behaving as a pure stick slip phenomenon. Pure stick slip phenomena mean that we have a fault, subduction zone in our case, where oceanic plate is subducting beneath the continental plate, and the deeper portion of the subduction second. Okay. Deeper portion of the subduction is constantly creeping, loading the shallower portion of the subduction, which is stuck together, and once every few hundred or so, the energy released in those megathrust events goes causing these devastating tsunamis and earthquake. Of course, we have some complexity on top of the aftershock, background seismicity, but the majority of the energy in this system released in those very devastating events. 25 years or so, we have two observations from two parts of the world that transform how we view faulting in general, those coming from subduction zone. The first of those observations came from the Cascadia subduction zone, which we're going to talk about all throughout the talk, so it's worthwhile to explain its tectonic settings. So we're talking about the Pacific Northwest, where we have the oceanic Juan de Fuca and Gorda plate, which are relatively young oceanic plates, subducting beneath the North American plate to the east. In 25 years or so, we have a new observation system, a geodetic network of GNSS stations, GPS stations, similarly to what we have in our phones, that will record very precisely the location of the station every day. And we expect that those stations will have the general motion of the tectonic plate, so the station should move constantly to the east. But what scientists immediately saw, that every year or so we have a transient reversal in the motion of the station, which moved westward instead of eastward for a week or a few months or so. This reversal in the motion of the station was related later to slow sleep in the deeper portion of the subduction. And I'm calling it slow sleep and not slow earthquake, because those are not earthquake. They are not producing seismic waves. At the same time, in Japan, new types of earthquake have been discovered. In classical records of earthquake, we expect to have a very indicative wave arrival with P and S wave and very indicative frequency contact. At the beginning of the millennia, a new type of earthquake has been discovered in Japan, where we have a signal which is a little bit above the noise level, and we don't have those very indicative phase arrival. And this signal was familiar for volcanic region, but those signals were definitely from the subduction interface. They were initially called non-volcanic tremors, and then more familiar with tectonic tremors. And they were at start very hard to detect, but through the years they are become much more detectable with machine learning, etc. And now we have catalogs of hundreds of thousands of those events from essentially almost any subduction. So those phenomena were initially discovered in subduction zone, but later they have been discovered also in transform fault system, the San Andreas fault, the East Anatolian and North Anatolian, and also in our Dead Sea fault. That's just to mention that we're talking about phenomena that transform how we view faulting in general. Now we have a spectrum of sleep behavior, and we will not talk about strike sleep fault anymore in this talk. So those two behaviors later have been found to be very, very highly correlated, both in time and in space. So here we're looking on a GNSS time series where we have, it's a longer time series than before, and we have many of those reversals. And those reversals are very highly correlated with increased tremor activity on the subduction. This is from Cascadia. This is also from Cascadia, and we can take those reversals from few stations and invert it for the location of the slip on the subduction. We can also locate those tremors, and we find that they are on the same region of the subduction. So the general mechanism thought to control this behavior is having a region of the subduction which is transiently slow sleeping, and we have some strong asperity on this region which is breaking during this slow sleep and creating those tremors. What caused this slow sleep is interaction between a liquid and the fault interface. We are talking about a subduction zone where the subducting plate is diving into the earth and at some point is experiencing a metamorphism which exhumes a liquid from the rocks which travel up. These liquids arrive to the fault zone, and it increases the pore pressure. The pore pressure is acting against the pressure from the column of rock on top of the fault, and essentially it's creating the effective normal stress to be very low. With effective normal stress, with low effective normal stress, small shear stresses can shear the fault and slip aseismically. So now we can have a modern view of a subduction zone where we still have the shallow lock portion. This is the portion that accumulated strong stresses in the interseismic period and released them in those very large earthquakes. We have the deeper portion that slip constantly and loading this system, and we have an intermediate zone that have those transient slips events and essentially transmitting stresses from the deeper portion to the shallow portion. In order to understand the entire system, we must understand the role of this slow slip zone. We can take the data-driven approach. We can start with essentially GNSS, or the prime data that we have on those events, and try to understand from it what the physics that control this event. This is valid. We got a lot of information from this, but this approach is limited because we're talking about the deeper portion of the subduction. Essentially, when we're trying to take data from the surface and understand what's happening deep into the crust, we're losing information as 1/r², so very fast. And the resolvable information is very limited. So we can take the other way around, which that's what we're going to do. We can start with the physics that we control, that we think control those events, and from that go to the observation. The underlying model which will control our numerical simulation will be rate and state friction model. It's a fundamental model throughout earthquake science. You will find it almost everywhere when people are trying to understand the mechanics of earthquake. And in its most simple form, we have a block, a slider that is sitting on a frictional surface. This block is pulled by a spring, which is itself pulled at a constant rate. The constant rate represents the motion of the tectonic plate. The elasticity of the spring represents the elasticity of the crust, while the contact between the block and the frictional surface represents the fall. The key feature of this model is its frictional law, where the friction is dependent on both the velocity of this block and some state variable. It's an empirical law. Well, this state variable, which is an empirical variable, we can think of it as representing the history of contact between our block and our frictional surface. So now we want to have a Cascadia-like model. We will have it by building a 2D domain, which will be bisected by a 10-degree thrust fault. And this thrust fault will contain 10,000 of this block spring slider model, which are all coupled together. In order to progress this model in time, we need to solve all of those interactions, and then to solve how those interactions impact the elasticity of our medium, which have 20,000 elements. So this is taking a lot of computational time, running one of those models taking about 4,000 CPU hours. We will introduce a slow slip into this system by applying some low effective normal stress to some region of our fault. The width of the region will be W, and the effective normal stress will be sigma W. We will change these two parameters through our study, essentially to learn how they impact the characteristic of slow slip. One final parameter I need to introduce is W over H star. This is the characteristic or the normalized fault length, seismogenic fault length. W, it's our W, and H star is the characteristic length at which a slow slip or earthquake start. This is used throughout the literature to see how this parameter control characteristic of earthquakes and slow slip. We will use it to compare to previous studies. So here is how one of our simulation looks like. We're looking on a progression of time along the y-axis. progression in space along the 4D on the x-axis, and here we have 4 profiles along those lines. We can find slow slip in our simulation by having some threshold. When our fault crossing this velocity threshold, we declare we have a slow slip. So here is one of our slow slip, and I didn't mention that to the left we're looking on the simulation of a function of time, and to the right we're looking on the exact same simulation of the function of time state of simulation. So here we have one of our slow slip, and these two views of the same simulation come to emphasize that when we're looking at the simulation as a function of time, this slow slip itself is essentially just a fraction, one thin line in the simulation. And when looking at the function of time step, this is the entire black region. We have a nicer view of the slow slip event. Should not be surprising. This is the region where the velocity on the fault is changing very rapidly. We need smaller time step in order to resolve it, and we have many time steps in those slow slip events. We will take advantage of this notion later in the machine learning model. So here is one of our slow slip. Here is a second slow slip. Between them we have one slow slip cycle, and we can find all of the slow slip in the simulation. We have 21 in total, and 20 slow slip cycles in total. So we can perform 76 of those simulations, which cost about 200,000 CPU hours. And we can look on two characteristics. We can look on the characteristic time, in what rate those slow slip occur in our model, and on the maximum slip of those slow slip events. The maximum slip is a proxy for the moment or the strength of those events. And when we have this view, this recurrence interval and maximum slip as a function of the W over H star, we can think that both of those, the characteristic recurrence time and maximum slip, are linearly dependent by W over H star. We also can compare to a previous result of Leo and Weiss, which used completely different numerical scheme, which I will not get into, but should represent same settings, and they get about similar results. But we might want to go deeper just to look on this very high level parameter. In order to do that, we essentially need more model inference. So we can think that we can do x2, x3, extend the number of model inference that we have. But if we want to do x 100,000 of the number of inference that we did, this is essentially impossible with the current numerical scheme. So in order to perform that, we will follow the scheme that I mentioned at start. We will use machine learning to create a model surrogate emulator. And this is following the general scheme of having an Earth system model that you want to model. This requires many steps. You need to discretize your reality. You need to perform spatial and temporal integration and many other operations, which you usually do by using the most efficient algorithm that you know, feed them all into a large machine and running the simulation. This is limited, as I mentioned. You're getting output from the simulation. You can take this output as your data and use it to train a machine learning model that learns the relation between simulation input and simulation output. With that, you can approximate those models efficiently. I think that nowadays, when people say machine learning model, they immediately think about neural networks. We're not going to use neural networks in this study. Neural networks are excel when you have abundance of data. And we are limited in the amount of data we can produce. What we're going to use is a reduced order model approach, which I try to explain in the next few slides. So reduced model approach is somewhat similar to principal component analysis, which I assume some of you are familiar with. Principal component analysis is an operation when you have a cloud of data points, in this example in the XY plane, and you apply this principal component analysis, you get back the axis in this XY plane that explain most of the information in your cloud of points. Our reduced order model approach will do a similar thing when we will learn what is the most important information in our simulation. This is coming originally from fluid flow simulation. Well, people started performing those simulations, which are pretty heavy. They stopped at some point, took snapshot of those simulations, applied singular value decomposition. This essentially gives us a mode of the simulation which are most important, contain most of the information, and then they can drop all the other modes that they have. They have probably a few hundred modes, and progress the simulation only on those two modes. This save a lot of time. In order to understand how we use this reduced order model approach, we need to understand how we take the complex simulation of faulting and put them into a way which is digestible by this reduced order model scheme. And to do that, we need to understand what phase space of dynamical system are. A phase space of dynamical system are a way to have a geometrical representation of dynamical system. Here we have a simpler example than rate and state. We have a spring hanging, a block hanging from the spring. If we will release it, it will create a harmonic motion, and this can be represented by a perfect circle, and any point on this circle is the state of the system. Here we have a clash of terminology. This state has no connection to the state from the rate and state friction, but we can think that we can change the dynamic of this simple system by changing the size of this circle. So similarly in the rate and state friction model, we can have a phase space, and here we're looking on again on a more simple form of the rate and state friction model. Its physical form is to the left. In the middle, we're looking on the velocity as a function of time, and to the right, we're looking on the phase space of this system. It's the velocity as a function of the state variable, and immediately we see that in its phase space, it has a much nicer form. Well, it's following this loop-like structure. If we will release it to motion, we will see the notion that in time domain, most of the time is spent in the not interesting inter-seismic or inter-SSC region. Well, in its phase space, most of the distance along this loop is spent in the more dynamically interesting region of the slow slip itself. So, in the next slide, I'm going to show the entire reduced order model scheme. It will contain many stages and mathematical operation, but following having this, we'll have a machine that giving some width and effective normal stress along the fault and some time. What is giving us is one state along those loops, one state of our rate and state friction model. We, of course, we're not in 1D, we are in 2D, so we have many of those loops, and we can infer that not in one time, we can infer it in many times, and reconstruct those loops, and from those loops, we can reconstruct our simulation. So, the scheme following is as follows. We start by data collection, performing the simulation with different width and effective normal stress along the fault. This is giving us a stack of simulation, and we're doing that in a manner that we have a fixed number of slow slip cycles in those simulations. Then we can split those simulations into individual cycles and perform the same scheme on each individual cycle. We can view the individual cycle in its phase space, in those loops, and then we can learn the shape of those loops. I will not get into how we learn them. It involves some spline interpolation, but the amount of technical detail I can convey in one talk is limited, and we learn the shape of those loops. This giving us the opportunity to transform those loops to vectors, column vectors. We now have a data matrix when each of those columns is corresponding to one width and effective normal stress on our form. We then can apply a classical reduced order model scheme. We are applying singular value decomposition to decompose this matrix. This is giving us a U matrix, an F matrix of coefficient when we can rebuild any one of those columns by applying those coefficients to the U matrix. And finally, we can interpolate between those coefficients to get new value that we want. So this is the offline stage, is heavily dominated by just calculating this stack, which took us a few 100,000 of CPU hours. Following doing that, we have the online stage, which include interpolating the line of coefficient that didn't exist. From that, getting a new column. From the new column, rebuilding the simulation, and then concatenating it to one continuous simulation. This takes 1 CPU minutes, and it's a reflect acceleration of a few 100,000 compared to the full physics simulations. In order to validate that, we have two approaches. The first approach is a leave one out cross validation, where we're taking one of our simulation from the stack, performing the entire scheme, and then calculating a reduced order model simulation with same value and comparing the two. The other is having a test set, 7 simulation that we put aside. We don't touch them in building this entire scheme, and only use them afterward to evaluate our performance. And here is one of the results. We have the forward order model to the left and the reduced order model to the right. And we can see that the reduced order model succeed to reproduce the forward order model very accurately, very satisfactory, both in the profile and in the spatial domain. Well, when we're looking on the characteristic of those source events, the recurrence interval and potency, which is a different, more accurate way to a proxy for the moment of those events, we're essentially getting the same number. So very accurate result in this example. We can compare over the entire 76 leave one out cross validation and 7 simulation of a test set. And in the recurrence interval, we're essentially getting great result all throughout. Both R square are very high. When we're looking on the potency, we're getting overestimation of the reduced order model, the potency of the events. This is an undesired result. We think we know where it's come from. We can talk about it and what we think needed to be done in order to fix it in the end. But what is still okay is that the relationship between the reduced order model potency and the physics-based model are linear. And it's pretty easy to correct that by just a simple linear correction. We can evaluate the linear correction on the leave one out set and test it on the test set. This brings the test set to also very high R square. So we're pretty sure that we're getting both the recurrence interval and the potency against the moment of those events very accurately, with just a fraction of the cost. So now we can take advantage of this model. And the first thing that we can do is just parametric exploration, where we can evaluate our model with 10,000 different width and effective normal stress. Doing so with the forward order model will cost 40 million CPU hours. And when we're looking on the recurrence interval and potency as a function of this normalized slow slip zone width, it seems again that we have some linear relation of those two variables in this parameter. But we now can have a deeper view. We can look on the width and effective normal stress plane and the function of those two variables in this plane. And when we're looking at the recurrence interval, we need to understand first that this value, W over H star, is changing by a factor of 6 between 1 and 6 megapascal of the effective normal stress, and by a factor of 2 between 30 and 60 width of the slow slip zone. And here we see that we would expect that it will change primarily on the effective normal stress axis, and this is a general view, but we have a band of very rapid change in the recurrence interval, which is along the W axis. So not along this W over H star parameter. We think that this is coming from including more portion of the fault, which is able to produce fast earthquake, runaway rupture in our slow slip region, and crossing some critical zone. Okay, so this is nice. We're getting some nice results. We can perform many models, but in theory, this is still possible to do with a forward order model. This 4 million CPU hours in a rule of thumb will be equivalent to $4 million in cost, and if you have it in your back pocket, you essentially can do all of those 10,000 models in parallel and finish with that within 1 week and have the same view, even a better view, because it will be more accurate running the physics-based modeling. But some processes we will never be able to do with just our physics-based modeling. And those are the processes or the algorithms that are inherently sequential in process. One of them is a Markov chain Monte Carlo algorithm, or a way to infer the probability of our parameter, and we will explore that. So in order to understand why we want to explore that, we need to go back to our reality. Here we have a reminder of our tectonic settings. I don't know if you remember what we're talking about Cascadia subduction zone. We have the Gorda and Juan de Fuca plate subducting beneath the North American plate, and we have this region of slow slip and tremors on the deeper portion of the subduction. The Cascadia subduction zone is known to be characteristically segmented to 3 segments, north, center, and south segment, and this is evident by different geological parameters of the outer wedge of the continental plate, the age of the subducting oceanic plate, and a geophysical parameter, the coupling. We will use the coupling in our model, so it's worth to explain what it is. A coupling is a parameter on a fault, which can go from 0 to 1, and it's telling us how the two sides of the fault are stuck, coupled together. So the shallow part of the fault, which we talked about, it should be stuck. The coupling should go to approximately 1. The deeper part of the fault, well, it's constantly creeping. The coupling should go to 0, and in the slow slip zone, on the long term, it also should go to 0. But this coupling parameter is actually heterogeneous along the fault, and we can actually see it when we're looking on a coupling model of the Cascadia subduction zone, where some region, shallow region, do not have a coupling of 1. And slow slip themselves now are also segmented into this north, center, and south segment in the Cascadia subduction zone. So here we're looking on the moment rate of slow slip as a function of latitude and time along the Cascadia subduction zone, and we clearly see there is a different characteristic behavior in the north, center, and south of Cascadia, and we can extract from this plot the characteristic recurrence interval and moment of those events. Well, we're getting 14, 20, and 7 months recurrence interval in north, center, and south, stronger event in the north and weaker in the center, and scattered event in the south. And in order to take our model and model those events, actually it's impossible to model the event in the center and the south, because our model do not take into account coupling. And we can introduce to our model coupling, which essentially modulates the strength of the event in our Monte Carlo Markov chain inversion. And why we cannot use forward order model with our Monte Carlo Markov chain inversion? Because as I I mentioned, this is an inherently sequential process, and it's done by having random walk on our parameter posterior distribution, where it's guided by our observation, in our case the recurrence interval and a moment of those events. And essentially we need many steps around of those random walk in order to converge to this distribution. And in this very simplistic example, it's very in favor of the forward order model. Here the difference in inference time is x15, where in reality is x hundreds of thousands. Essentially to be able to converge to our parameter distribution with the full physics-based simulation will take decades. So what we are doing is taking the recurrence interval and the moment of the events here in northern Cascadia, and we are applying the Bayesian inversion or Monte Carlo inversion in order to get the effective normal stress with and coupling in northern Cascadia. To do so, we perform 40,000 reduced order model inference, where this is equivalent to 45 years of full physics-based modeling, which is obvious why we will not do that with full physics-based modeling. This, on top of giving us the expected value, giving us also the confidence in those values, assuming our modeling settings. We can do this in the north, center, and south of Cascadia to get a probability distribution function to those three parameters in those three regions. Well, what we're getting is we're getting an effective normal stress of 2.7 in the south, 4 in the north, and 6 in the center. This is very low effective normal stress. Essentially, it means that the pore pressure is almost the lithostatic pressure, but those differences we would essentially never be able to infer them from observation we have from the Earth surface. And this is why we started using a physical-based simulation, because some physics we will just not be able to infer from what we can observe from the Earth. But we have the coupling. In coupling, we're getting that the coupling in northern Cascadia is about 20% higher than the coupling in central and southern Cascadia. And this should be we should be able to observe this difference in coupling with our geodetic network system. And this is what we done. We took the geodetic network in Cascadia, and from that we extracted the inter-SSE's velocity, so the velocity only in the part not including the slow slip itself, these red parts. I will not get into how we done that. This is not the point of the talk, but it's somewhat related to the connection of those slip events occurring when we have a large ETS production on the subduction. We can also take the long-term secular velocity of those GNSS stations. This is we can take just from the literature, and now we have two velocity fields in Cascadia. One of the velocity between those slow slip events, and one the long-term velocity. We can take that and invert it back to the coupling on this slow slip region. And we're getting this final picture of having the long-term coupling to the left, the inter-SSE coupling in the center. Both are geodetically derived, and comparison between the geodetically derived coupling and the reduced order model physics-based coupling. We're getting that the inter-SSE's coupling, the reduced order model coupling, which also should present the coupling between those slow slip events, have a very nice agreement in all segments. And this is reassuring in our modeling setting. What we can also do is compare the now coupling that we are more confident in of the inter-SSE period and the coupling in the long term, where we see that in the south, the coupling in the long term is 0, which means that the slow slip in that region release the entire energy in the slow slip zone. Well, in the north and center of Cascadia, the coupling in the long term is not zero, and the slow slips themselves not releasing the entire energy on the subduction, and the strain or stresses are accumulated in the long term and should be released at some point in the future, maybe with a megathrust event penetrating to this region, or a larger slow slip event, or something else. I will finish with a summary. We talked all throughout this talk about what slow slip events are, why they're important, and why we want to understand them. We developed a reduced order model scheme, machine learning scheme, in order to approximate a physical-based simulation modeling those slow slip events. We use it for a parametric space exploration and for a Monte Carlo Markov chain inversion in order to invert for the physical properties controlling those slow slip events. Thank you.
Questions?
Thank you for an interesting talk. Can you go back to your slider block model slide? What is this eta V? It's a viscous, the first equation.
Well, this is a dumping coefficient, radiation dumping coefficient.
So
No viscous in
but
those models.
it is a viscous effect. It's a damping.
Yeah. So yeah, I'm not sure it's represent. Okay.
So what do you think of the idea that has been suggested by Vieska and others, and about slow slip is emerging from coupled viscous Bernoulli deformation with patches of viscousness actually controlling the degree of slow slip?
Without low effective normal stress?
No, with low effective normal stress, but it actually, this low effective normal stress that you show, it's very low, right?
Yeah, it's very low.
Extremely
It's
low.
extremely low.
It's like having it nearly
zero.
Yeah, nearly zero. So I think those models might require less,
Okay.
less or higher.
Okay.
So I was.
I'm not familiar with those models. Vieska? Yeah,
Yeah.
I know. I'm not familiar with those models.
So your
Understand.
control parameters are W and normal stress. Those
Mhm.
are the only
Two
two
control
control
parameters
parameters.
in those in these settings.
There was another question in the back.
What is the difference between the single value decomposition and proper probability decomposition? POD and SOD?
What again?
You in a previous slide maybe
Applying the singular value decomposition.
in a where you are showing the reduced order model. Yeah. So you get at the point number 5, the single value decomposition and a proper and probable decomposition. So how in both we arrange the data in the same way or in a different way?
How do I?
Difference between the single value decomposition.
Okay, proper order decomposition is just multiplying the sigma by V transpose, and then what you're getting is this coefficient matrix. It reduces the size of the matrix, and then you have U, which is spanning this data matrix, and you can apply each row of this coefficient matrix to this column vector in order to rebuild any one of these column vectors. I will apply the first row on this column vectors. This is a linear combination which will recreate this first data vector, and I will apply the ith coefficient row to this matrix to create the ith data vector.
How it differs from POD?
How it?
Differ from POD.
From POD. This is POD.
Oh.
This is POD. This is SVD.
Oh, And so SPD is the part of your.
In order to calculate proper orthogonal decomposition, you apply singular value decomposition and then you multiply sigma by the principles.
About your 40,000 simulations as the realistic scale, what are your priors for the MC simulations? Maybe I didn't get it. I mean,
we have just a uniform prior on our parametric. So we have some sampling of our parametric space. Or this is.
It's again the normal stress and the.
So we have those values between
Yes.
1 and 6 and 30 to 65, and we have uniform prior along those two axes.
Uniform. And how these numbers were determined, like 1 to 6 and 30 to 65, from the
I will correct myself, because in order to reproduce the central Cascadia, we actually needed to extend these values up to 10.
Okay.
This is a later study, which I didn't show the figure, but in order to essentially have a combination of parameters that can even reproduce the observation, we need those values.
Okay, so you have a physical model, physical-based model,
Mhm.
from which you get a range of
Yeah,
probable parameters,
yeah.
and these are used as priors for
Yeah.
your ROM
I
simulation.
have here a polygon that on those two, a polygon that can reproduce my observation, but which point in this polygon is the most probable? That's what I'm trying to get with the Monte Carlo
With the
object.
Okay.
Can you go back to the W over H plot relatively in the beginning?
This one or the
No.
first one?
Showing the dependence on W over H.
It's shown also here and also here.
Yeah. So you mentioned that there's more or less a linear dependence on W over H, but it does also show that those yellow dots there that simply don't not being dependent on WH. Could you explain the physics behind that?
Yeah, so we essentially so we have WH star can be just we have some we might be able to create like smaller recurrence interval if we decrease W over H star with a specific effective normal stress. This will require to have smaller and smaller width. And this width can essentially, at some point, we have an important point in our model, which I didn't mention. At this point is a point where the fault is transitioning between this region where it's velocity strengthening. This is the region which the fault in general tend to produce fast earthquake. In this region, which the fault is velocity strengthening, which the fault in general tend to create a creep. And if we will reduce our W to contain less and less portion of the velocity strengthening part, it will at some point will just produce constant creep.
And just another question. So you're basically describing a way to produce some form of digital twin or digital emulator of a physical environment, and then that essentially saves you time instead of running the whole second simulation. Already it saves you time, and then. But so what would be the fundamental questions that then you can ask these simulators?
We show how we derived coupling. I maybe didn't emphasize enough, I think, the importance of coupling models in earthquake hazard assessment. Coupling telling us where our energy is stored in our fault. And where our energy is stored is when we know where energy is stored, we know where the energy will be released and where devastating earthquake will occur.
So for predictions of earthquakes and the like.
prediction is a strong word in the earthquake world. I would say better hazard assessment.
I have a question. Can you go to where you talk about coupling at the end?
Sure. The final slide?
Yeah, the final few slides where you show kind of the results from coupling. So you show basically that there's different regions of coupling in this fault zone. Some areas of high levels of coupling, some areas of much lower. So I think for me the question is, what are the physical parameters that are controlling the coupling? What are the physical processes? So I think are we talking about the friction on the fault? Are we talking about rheology? Are we talking about temperature control effects? What are the physics behind this coupling?
Those are very good questions. I'm not sure they have a definite answer. But we showed, or I showed like in a different slide, that we have a segmentation in Cascadia that is following many geological aspects. One of them is the age of the subducting plate. So here in the south, the age of the subducting plate is much younger than in the center and the north.
But that's not a geophysical parameter. I mean, so
Right, it should
but,
be the viscous deformation,
right.
but actually is,
But it's reflecting through the temperature of the subducting plate.
right.
which is the viscous
Yes.
deformation.
That one.
The temperature is the viscous
Yeah.
deformation, which should be actually entering into the model in some way
Yeah.
to explain exactly.
Yeah.
In a more
I
complex
agree.
model.
I
In a
agree
more complex
that
model.
in general we need to add viscous. We can make those models more and more complex. It will become more and more expensive than what we have so far. So yeah.
Any more questions? Okay, so it's Stanley speaker again.